Hello and welcome to Lecture 27, our final lecture on optics, on the topic of optical devices. But let me speak for a second to the fact that this is our final lecture on optics. The unit of introductory physics that covered optics for us and through these lectures began with treating light as a wave and discussing its wave-like phenomenon through the interference of two source waves, and then eventually more broadly with many source waves. But that journey continued through talking about image formation, refraction, and reflection, and now culminating in a very applied physics chapter, talking about some specific human instances or human devices of corrective lenses for the eye, microscopes for looking at things small, and telescopes for looking at things far away. Okay, so let's conclude optics with optical devices. What are my two objectives here? Well, we want to learn the optical differences between farsighted and nearsighted, okay, these two types of eye ailments, and the meaning of a diopter for those corrective lenses. And we're talking here about reading glasses, contact lenses. We also want to learn and understand the appropriate formulas for image formation. All right, so talking about images, or I'll also be talking about images for those glasses, by compound microscopes and telescopes, specifically refractive telescopes, but I'll define that down below. And these are devices composed of a pair of thin lenses. Okay, so we should expect to use the thin lens formula. I'll at least an approximation of it, but we'll get to that. Now, this whole chapter, I should say up front, as we get into the key terms, and we have a whole page on the key formulas, is a very mentally taxing chapter for me to teach because it's very heavy on the definitions. However, it is very light on the mathematics, or at least fairly light on the mathematics. So those are things to keep into to account. Okay, so let's take a look at our first key terms: the conditions of farsighted and nearsighted, and or you could say farsightedness and nearsightedness. Farsighted, so someone who is farsighted has hyperopia. Someone who's nearsighted has myopia. Okay, so what's going on with these conditions? Well, let's take a look at the pictures as well as the definitions. But first, let's note that these here represent myopia. It's nearsightedness. And the correction for myopia is shown here. Okay, so this is the correction for myopia, a kind of zoomed out version of how the correction works and how it redirects the rays in order to achieve the correction. And then here showing specifically what the correction does with the lens, the corrective lens, to the rays within the eye. But what is happening here? Well, first of all, it's good to note that the correction for myopia, nearsightedness, is a diverging lens. A diverging lens, as we can clearly see, thinner in the middle, thicker on the ends. Okay, so that means it's going to cause the rays to partially diverge. Of course, the human eye has its own lens, and that's going to converge the rays no matter what. So this diverging lens, you can think of it as diverging the rays until they contact the converging lens of the human eye, where they eventually get all shined onto a single focus. All right? All right, on the other hand, we have hyperopia, farsightedness, and what is it corrected by? Well, as you can see, this type of lens here, thicker in the middle, it's corrected by a converging lens. Okay, so the corrections are diverging and converging for myopia and hyperopia, respectively. But more about the conditions, let's take a look. Oh, excuse me there. Farsightedness, hyperopia, is an eye condition where the lens is too weak or the eye is too short. All right, so the lens is not focusing the light enough or the eye is simply too long. So zoom in on that. So lens, all right, so we have here with hyperopia, hyperopia, lens too weak or eye too short. See, we have a shortened eye. What does that result in? Well, you can see from the ray diagram, that's going to result in an image formed behind the eye. What type of image? A real image formed by the converging lens of the eye. All right, that's always the type of image that's being formed in the eye. And since it is a real image formed by the converging lens of the human eye, well, it's always going to be a real inverted image. Right? Everything that's actually going to land on the specialized cells for detecting that image on the back of the eye, right? If they land in the correct spot at the back of the eye, well, then that signal is going to get sent to your brain, but it does come in upside down. It's just we flip it right side up, whatever that that means for our impression of the world around us. All right. And one other line of information about farsighted, it means that it is a difficulty in seeing objects up close. Okay, so I want to pause on that just real fast because it's called far-sighted, but it refers to vision up close. Because someone who's far-sighted can see well far, but they can't see up close. Okay, so it's implying that you can see this well, but you can't see things up close. All right, and we can tell by looking at the ray diagram because far-sighted shows parallel rays. So you notice the parallel rays coming into the eye. Parallel rays imply in ray diagram nomenclature an object that's far away. Because if a source of these rays is very far away, then by the time the rays get to the eye, they're essentially parallel. Okay? But what about nearsightedness? Well, based on the naming convention here, we can guess that nearsightedness is someone that has difficulty seeing objects far away, because it means you can see okay up close. All right? So it is an eye condition where the lens is too strong or the eye is too long. All right? So it's just the opposite of farsighted. And it results in an image formed in the middle of the eye, right? Before we saw the image being formed behind the eye without correction. And if we zoom in on myopia, we see that the image here is being formed in the middle of the eye. There's no cells there to detect it. So by the time the image gets to the detective cells back over here, it's not in focus, which of course was the issue here too, is the image would not be in focus. There'd still be something there. There'd still be light. After all, it's a real image. There's photons. It'd just be blurry, right? And then, as I said before, myopia is difficulty in seeing objects far away. Right? So enough about nearsightedness and farsightedness for now. We're going to get on to the idea of microscopes and telescopes. However, to be fair, this next term, angular magnification, actually applies to all of our systems. Whether that's corrective lenses for nearsightedness or farsightedness, or it's microscopes or telescopes. Because that's one thing that all these ideas have in common is, at least most of the time, we're going to be talking about angular magnification. Now that's different from the type of magnification we talked about in all of our preceding lectures on image formation, okay? So we just had 4 lectures about image formation, and every time there we talked about magnification, the M magnification factor, as being equal to negative of the image distance over the object distance. That was often the way we'd find the magnification. What that actually meant was that the image height over the original height was equal to that factor. So if the magnification factor was 2, the image was twice as tall. We also had a meaning attached to the sign, because if the image was negative, it meant that the magnification was negative. It meant that the image was inverted, flipped upside down. And if it wasn't negative, it meant that the image was upright. Right? So this negative is really part and parcel of all of the sign conventions, because we wanted our images to represent whether they're upright or not. Okay? But now we're not going to be talking about magnification as a ratio of image height over height. Instead, it's going to be angle of the image over angle of the object. Simple as that, right? So it's a ratio of the angle subtended by an image to the angle subtended by the object, okay? Now, that has different effects. Right? For example, you can refer to the previous lecture on the images formed by mirrors and see how a rear view mirror, which is a convex mirror on an automobile on the passenger side, creates images that have heights that don't match with our perspective of which images are larger or smaller, at least when you compare that driving mirror to a planar mirror. So that was kind of hinting at this idea of angular magnification, an idea that will be formally represented here in this lecture. Okay? So now finally, microscopes and telescopes. So a microscope is composed of 2 converging lenses. Okay? All right, so two lenses, they both converge light. All right, both capable of creating real images and virtual images. Okay? So think about converging lenses, they are capable of creating both types of images. Okay? The lens near the object, right, the thing that's maybe on your slide in your microscope, is called the objective lens. Okay? So there we have the object, there we have the objective lens, okay? You can see in the picture. The lens near the eye is the eyepiece, right? So that's never really called the eyepiece lens, just the eyepiece, right? So that's this lens up here. So there's always 2, all right? And both focal lengths should be short, all right? In order to build an effective microscope, you're gonna have short focal lengths. How short? Well, just much shorter than the distance between them. In fact, we can define the distance between the object or the objective lens, so right here, the objective lens, with the eyepiece, we can define that as L, okay? Which I thought I had defined here, but I must have, anyway. So this distance here is L, right? The distance between the two eyepieces. Now, however, right, this right here, this statement, both focal lengths should be short, that's something that we better back up, right? And I'm going to back up why that's the case, why it's beneficial to have a microscope where both focal lengths are short. Because otherwise, this is just a rule we have to memorize that doesn't make any sense. But of course, in this class, we'll try to make sense of it, and we're going to use our background information about images, use some particular approximations for the microscope, and come up with the reason of why both focal lengths should be short, okay? So one thing to note about the microscope, and we'll say more about those approximations, right? The approximations of both the microscope and the telescope is a big part of the important ideas here. But one thing we should say up front is that the object, the thing on the slide, for example, is near the focal length of the objective, all right? Right away, that, well, kind of the meaning of short is that if this is the focal length of the objective, then, it's that image, or rather that object, is very close to that focal length, all right? Okay, but what about the refracting telescope? So again, it's gonna have two lenses, right? So you have a lens here and lens here. What type? Well, turns out the same type. So the telescope is also composed of two converging lenses. So that's really interesting because these do very different things. Microscopes, small objects; telescopes, huge objects, often stars, but very far away, or planets. But they both use a pair of converging lenses, right? I guess it just is a testament to the versatility of converging lenses. Okay, now, just like the compound microscope, the refracting telescope has an objective lens and an eyepiece, or an objective and an eyepiece. Now, here we have a different rule, again, one we will justify. The objective focal length should be long, all right? And the eyepiece focal length should be short, or at least much shorter than the objective focal length, right? And we're going to have some focal point right there. So you can see there's rays converging right at that focal point. So that's kind of a hint at one of the approximations. We're going to assume that, it's actually a very good assumption because we have parallel rays coming in to a converging lens. We've seen this before when we introduced images formed by lenses, that when you have parallel rays coming to a converging lens, the image that's formed is at the focal point of that converging lens. So that right there, that's our long objective, right? That's our F for the objective, the focal length, okay? Okay, so let's get on to our key formulas. Oh, let me take a look at something, excuse me. So let's see, there we go. The object is far away in this case. All right, so before we had an object that was close to the objective length or the focal length of the objective. Here, our object is very far away. It's essentially infinitely far. S is infinity. Okay, now we're ready to move on to our key formulas. Let's take a look at those. So we're going to have key formulas that apply to corrective lenses for myopia and hyperopia. Right, not much to say there, but we will have some interesting examples with them. But again, you can see it's pretty straightforward. This is defining or writing variables. Then we're going to spend a while defining what is meant by angular magnification. This is an important idea. It's simple on the one hand, because it is just a ratio of angles. On the other, we ought to pay attention to some of the subtleties, and I'll call attention to the two cases of angular magnification, because it turns out there are two distinct cases with slightly different values of angular magnification. All right, and then finally we'll get into particular formulas, approximations that apply to microscopes and telescopes. And in both of these, I could have an approximate symbol, but instead we'll just define it because we're saying that this is kind of the definition. We're just considering it an equation, but it is absolutely an approximation. Okay. All right, and of course we have some further pictures to describe all the ray diagrams, which helps cement this idea so we really understand what's going on with the light. So first, our first equation. This is the equation that's used for myopia and hyperopia, and all it is it defines what optical power is. So optical power is the variable, and the unit is the diopter. Okay, and when this unit is expressed, we always just write out the word diopter, or we could define it as inverse meters, because after all, a diopter is exactly an inverse meter. Not an inverse centimeter, by the way, but an inverse meter, because it's just 1 over the focal length, which is a distance measured in meters. Okay, so that's it. Optical power for corrective lenses is a commonly used variable, so we need to define it here, but obviously simple to calculate. Now this next term here, this uppercase M, this is magnification, but it's angular magnification. which is why we're distinguishing it with an uppercase M as opposed to a lowercase m, which we used for absolute magnification, which of course was h prime over h. Okay, that one is all about actual physical heights. Here, where this is about the angles. Okay, but they're different values, right? You can have a situation where you have a large absolute magnification, but a small angular magnification. So they don't represent the same thing. Okay, so but let's just look at how we define it. So angular magnification is the ratio of angular size of the image measured in degrees or radians to angular size of the object, also measured in degrees or radians. Okay, and this particular expression, this one here, that says that angular magnification is always 25 centimeters over f, that expression is specific for a situation called the relaxed eye. Now, again, this might seem like an arbitrary definition. What is a relaxed eye? But a relaxed eye is when you have made the biological converging lens of the eye allow light to come in as parallel light. So you're focusing on something as far away as possible. It's relaxed because it has the longest focal length, where it's going to take in those parallel rays and focus them on the back of your eye. And that's the idea for relaxed eye vision, because it puts the image infinitely far away, right? Or at least, so much further away to the scale of the eye that it's effectively infinity. And in that case, the focal length is exactly equal to the object distance, okay? So the focal length is equal to the object distance for the relaxed eye, all right? Okay, so why this 25 centimeters? So this 25 centimeters represents the near point of the eye. And to further understand that and angular magnification in general, let's take a look at these two figures down below with our inchworm on a leaf near a flower, okay? So when the inchworm is at the eye's near point of 25 centimeters, its image on the retina is as large as it can be and still be in focus. At the near point, the inchworm subtends an angle of theta. All right, that's its angular size. All right, that's the angle. It says subtending an angle and having an angular size mean the same thing. And real quickly, this idea of the near point, that is always 25 centimeters. That is agreed upon value. It's an average for an eye that doesn't need correction. That's the closest thing you can hold to your face and still focus on it without it becoming blurry. All right, 25 centimeters. Okay, so there is the human near point, taken to be 25 centimeters. The physical height of the worm is y. Okay, so what we're going to do here is we're going to define that angle as just y over f. All right, now this is a small angle approximation, because here we're saying that theta is approximately tangent of theta is approximately sine of theta, the small angle approximation. And the small angle approximation is what allows us to write our angular size as simply y over f. Okay? All right. So there we have the actual size of the object. That's how much angular space the inchworm would take up for the naked eye, the unaided eye. But what if you used a converging lens, like a handheld, not microscope, but a looking glass for looking at things up close? Okay? So with a magnifier, the inchworm can be placed closer than the near point. Whereas before, if you placed the inchworm closer, it would not have been focused. Okay, so you're gonna be able to place it closer and still focus on it. Because what the magnifier does is it creates an enlarged upright virtual image. Why? Because the inchworm here is within the focal length. In fact, we're going to assume that it's just within the focal length of our converging lens, because as long as we put it just within, we'll create a virtual image. If we put it just without, then we would create a real image on the wrong side. But if we put this inchworm just within the focal length, or effectively at the focal length, it creates a virtual image where? Infinitely far away. See? The image is formed at infinity. When the object is placed at the magnifier's focal point, the image is at infinity. All right? And those rays, those parallel rays, are coming in to the relaxed eye. Okay? And in that case, now let's look at the angle subtended by the image. Well, we see that the angle subtended by the image is y over 25. All right? Or excuse me, y over f. Whereas before, the object was y over 25. I recently put a box around y over f when I was referring to this figure here, but that was a mistake, and you can see why, because of course my triangle, my opposite side of my right triangle over the adjacent side is y over f. Okay? Yeah. I said the wrong thing again. Y over 25 centimeters. And that's consistent up here because there we see that is the angle theta without the prime. So it's the original angle, the angle of the object with the naked eye. But anyway, here we have the image angle. But what's interesting about it is it's still y, right? But now it is y over f. Why is that? Well, let's look at the object here, right? We've placed the object closer than the human near point. So this distance here, s, is not 25 centimeters anymore. It's something smaller than 25 centimeters, right? And it's whatever your converging lens has been manufactured to have as its focal length. But if we look at this triangle right here, that forms a right triangle with one side of y, the other side of s, right? So we have y over, well, f. Y over f is that triangle. Now, what's that angle? Well, this angle right here is none other than theta prime, because the proportions of this triangle have to be the same as the proportions to that triangle. They're similar or equal proportion triangles. So then we get that the image angle, theta phi, is just, well, y over f. All right? So then, of course, the y's cancel, which is why now angular magnification is not dependent on the actual height. It's just the angles. And it just becomes human near point over the focal length of the lens. So kind of an interesting idea, all right? But very applicable to many situations. However, there was one assumption to make. It was the relaxed eye. Because it turns out that you don't have to have a relaxed eye. You could have an engaged eye. In fact, you could have an eye that is working as hard as it can be, an eye that's focusing on something that's as close to the eye as you can humanly focus, that human near point of 25 centimeters. So what happens if you still use a magnifier, but instead you don't relax your eye, you focus it as hard as you can? Well, in that case, you end up with a magnification, which is equal to the magnification of the relaxed eye plus 1. Let's see why. So note, magnification can also be done with the image at the human near point instead of infinity, okay? Right, so instead of s prime equals infinity. So in this case, we still have the same definition for angular magnification. It's always just theta over theta naught, or here the notation is slightly different. I did not notice that, but it should be theta prime over theta, okay? And so same argument where we have y over s, y over 25 centimeters, all right? But here's the thing. Here before, we canceled out the y's, so that's unchanged. But before we replaced s with f. We're not going to do that anymore. So I've cleaned things up here. I've cleaned up this fraction over a fraction to put the 25 centimeters on top, and I've rewritten s based on the image formula, which is our ubiquitous image formula. It just says that 1 over s plus 1 over s prime equals 1 over f. The way to relate object distance, image distance, and focal length of the lens. Right? For all lenses, converging or diverging. Of course, in diverging case, f is negative. But here, we've just replaced s with its expression from that formula, right? Okay, then we're going to clean this up one more time because this is a parentheses here raised to the negative 1 power that itself is in the denominator, which means we can bring it up to the numerator. And now we see that angular magnification is equal to the human near point times 1 over the frequency, or times the sum of 1 over the frequency, 1 over the focal length plus 1 over the near point. Okay, well, let's go ahead and distribute that near point value of 25 centimeters. All right, and the only thing I've done here is just say that s prime equals 25 centimeters, because you see here is a variable, s prime, all right? But here I've defined it as, well, actually specifically, I meant to write this, it should say negative 25 centimeters. Why negative? Because it's a virtual image. And always by the sign convention, virtual images have negative values. And we're forming that virtual image at the near point, so it should say negative 25 centimeters, which is part of the reason I put that in there, although I left out the negative. Excuse me, I'll fix that. But that's important because that's why this becomes a plus, right? But here's the interesting thing. Once we distribute that 25 centimeter value in, we then find that the angular magnification is 25 centimeters over the focal point of the lens, right? Which should look familiar because that's the result we got for the relaxed eye. But then we just have one more. We just get one more factor of magnification. So if the magnifier you're using, it's that some handheld magnifying glass, if it gives you 5-fold magnification when you're using, where you're letting your eye relax and you're just kind of looking to the lens and getting in focus, well, then if instead you focus your eyes, you engage your eyes and you try to look through the object and you try to focus on something as close as possible, and then which would then cause the image in the magnifier to become blurry. But then if you corrected for that by then moving it slightly, because now you're not, again, you're not putting the object at f anymore. You're putting it slightly off of f. But when you do that, you'd see that it's slightly bigger. You'd get it that much bigger. You'd have a little bit more increase because now it'd be 6 times bigger instead of 5 times bigger. Okay, so enough about angular magnification. We're going to go into microscopes and telescopes. Now, angular magnification will come back. It is applicable to both systems, okay? But there are some more specific details we need to talk about for microscopes and telescopes. And this is the bulk of the content here. The practice examples I'll show you in just a moment are simpler than introducing these ideas, all right? So here is the formula for the total magnification of a microscope, all right? The total magnification of the microscope. Big M, which implies it's going to be angular magnification, okay? And it's equal to the product, let me see here, the product M1 and M2, where M1 is the magnification of the objective lens, M2 is the angular magnification of the eyepiece, okay? So 1 for the lens that encounters the light first, 2 for the lens that encounters light second. 1 for the objective, 2 for the eyepiece, okay? And then it turns out that that magnification for the objective is just going to be negative L over F1, all right? And then the magnification for the eyepiece, the angular magnification, is going to be 25 centimeters over F2. And this should look like angular magnification because it has the human near point that we were just justifying that shows up in the definition of angular magnification, all right? Or the expression for angular magnification, right? L is the length of the microscope, so it's distance. There's that human near point. F2 is the eyepiece focal length, because 2 denotes the eyepiece, and then F1 is the objective focal length, okay? And we can see here that here's the objective close to the object, or the object is shown as O, right? So then we could say that 1 is equivalent to O for objective, 2, the second converging lens, is the eyepiece, so 2 represents E, E for eyepiece, okay? And we can see L, here's the L between the distance between the lenses that was mentioned in the definitions. All right, so L, that variable, is the distance between the two lenses, represented as the length of the microscope. Of course, the microscope would have to have some casing. It would be physically longer than this, but we don't care about that, right? This is a microscope with its length is only the distance between the lenses. Okay. All right. So now let's talk about where this formula comes from, because otherwise it seems a bit arbitrary. Okay. So note, we'll do a little derivation here. The magnification of the objective lens is just going to be S1 prime over S1, right? So it's just going to be the image distance over the object distance, okay? And here, I'm not showing the negative because I only care about the magnitude of that magnification, just its value. I don't care that it's what its sign is. I know it's going to be a real inverted image, okay? And then that means I can then rewrite this in terms of L and F2. Why is that? Well, because I'm saying here that S1 prime is going to be equal to L minus F2, because I'm forming the image from the objective at the focal length of the eyepiece. And if that's the case, then L is equal to the distance of the focal length of the eyepiece plus the image location of the objective, okay? Those two have to sum up to the total length, because the image is being created at the objective, F2, of the eyepiece, okay? That's where we're making the image. The reason for it is because if we make the image right there at the focal length of the objective, then that image is treated as the object for the eyepiece. The eyepiece will create the secondary image where? At infinity, for the relaxed eye, okay? So for the relaxed eye. All right, and then the angular magnification of the eyepiece is just going to be 25 centimeters over that focal length. Okay, so that means we could rewrite it. All right, all I've done here is just rewrite M1 using this definition as this, and then I substitute that in. Okay, and then I'm going to do the same thing. I'm going to just express the angular magnification of the eyepiece. It's just 25 centimeters F2. Okay, so there that is, and then I'll make my key approximation. All right, what is that key approximation? Well, I'm going to replace L minus F2 with just L. Because I'm going to say that the focal length of the eyepiece is so much shorter than the length between the two converging lenses that, well, we can just ignore it and just say it's equal to L. All right, it's a big approximation, but it works pretty well. It's very little percent error. The other thing is we're going to get rid of S1 completely, right? We don't want it in our expression. Instead, we're going to say that we're going to put the object, which is S1, in the original object, the actual physical object, right? Not the image being treated as an object. We're just going to put it right at the focal length of the objective, okay? Now, technically, that would create an image at infinity for the, for the objective lens, and that can't work because we need the image to be exactly at the focal point of the eyepiece. So our approximations are just that, they're approximations, but they work pretty well, and they're so crucial because look what it gives us. It gives us this expression, which here I am acknowledging as approximation. Here I just show it as kind of a rule. But look what we have now. We have a magnification of a microscope that's just dependent on the physical parameters of the microscope, the length of it and the focal length of the two lenses, and I guess that a human is using it, okay? That's great because that means it's independent of where you put the object. That means you have a lot more reliability, again, approximate reliability, but reliability of your device because it's always going to do the same thing. It's not dependent on what object you look at, okay? So interesting thing there. Of course, we know this is an approximation, so if you want to get really detailed results, you might have to correct for the fact that we did make these approximations, all right? Okay, and we'll zoom out a bit because we will be talking about the telescope in just a moment. But I want to add to this figure here, this ray diagram for the compound microscope, and just reiterate something quickly that I just said, that the diagram here shows accurate rays. Because look, it does show the image of the objective, which of course is the object of the eyepiece. It shows it not forming exactly at f2, right? And that's the case. It really does not quite form at f2. But we're going to say that it does, all right? And we're also going to assume that the object is not offset from the focal length of the objective, but instead is right on it, because again, that is one of our approximations. And here we can definitely see, right, because the scale here shows that L is substantially, it is not equal, to just S1 prime, that we can't just ignore F2. It seems like a substantial distance. Maybe it seems like it's about a third of L, right? But of course, in many of our cases, maybe F2, the objective of the eyepiece will be 1 millimeter, and then the distance between the eyepieces is 150 millimeters. So it would be a different scale here. It's basically drawn to this scale so we can clearly see the rays. Okay, so finally, the last equation here, the telescope. Okay, so what are our equations? Well, we've got the angular magnification of the objective, okay? All right, so that's just gonna be that one right there. Then we also have the angular magnification of the eyepiece. And this is really should say angular size, not magnification, right? So bad choice of words here. All right, that's my typo. All right, and then we also have the height of the image eye formed by the objective, right? So these are both angular, angular size equations. And here both times they're an image height because they're the image formed by the objective. Now, you might think, well, angular magnification isn't defined by image height, it's defined as by object height. Well, of course, that's because the image formed by the objective is being treated as the object by the eyepiece, and that's actually why it shows up both times here, okay? And then we can then, of course, cancel those out, and then we get that the final angular magnification of the telescope is just equal to the objective focal length over the eyepiece focal length. So in a purely just taking this equation at face value, we can see why we want to have a large value for the objective and a small value for the eyepiece. Because if your objective focal length is say 50 centimeters, and your eyepiece focal length is 1 millimeters, well, 50 centimeters divided by 1 millimeter is 50 divided by 0.1 or 500. That'd be a great magnification, right? So very long objective, very short eyepiece. But where does this equation come from? Why do we have this equation? Well, let's justify it a bit by taking a look at our approximations. And these are simpler, all right, for the telescope. It's a simpler case because we definitely have that the length of the telescope is just equal to the sum of the two focal lengths, okay? We don't have to ignore one of the focal lengths. We just have to say that the distance between the two lenses is exactly equal. So L is just exactly equal to the two focal lengths. So because we have something similar going on where we have rays coming in, forming an image at the location of both focal points, right? So it's forming an image at the exact location of the objective, and or at the focal length of the objective, at the focal point of the objective, and then we just line up the eyepiece so its much shorter focal point lies right on top of that that same point where the image was formed. Okay, all right, and why does that work out so well? Well, the important thing is that the rays are coming in parallel, which means that the original object is infinitely far away. And so that means that the image formed by the objective, the primary image, is exactly at the focal length of the objective. And since we're going to set the object distance for the eyepiece, S2, equal to its own focal length, well, that means we're going to have a final image, a secondary image, that itself is at infinity. So we had an object at infinity to start with, and then we finish with an image at infinity. Right? We come at infinity and we send it back out to infinity. But that means that when we look at the telescope, we're using a relaxed eye, and the object is at infinity, and the secondary image is there as well. Okay? And it's simply a matter of matching up those focal lengths. Right? So pretty simple system, but neat effect because you can clearly get a magnification with this idea. Okay, but it only works if your rays are coming in parallel. So you can never use this principle for a microscope because microscopes are looking at things up close. Those rays are definitely not coming in parallel. Okay, all right. So now finally, let's get to our example problems. 3 types. I bet you can guess: corrective lenses, microscopes, and telescopes. Indeed, that's it. So we have, for our practice, type 1 problems that involve image formation by corrective lenses for human farsightedness, which is hyperopia, and nearsightedness, myopia. Type 2, problems that involve image formation by compound microscopes. Type 3, problems that involve image formation by refracting telescopes. All right, so let's get to it. Example 1. The near point of a certain hyperopic eye is 232 centimeters, right, instead of 25, in front of the eye. Find the focal length and power of the contact lenses that will permit the wearer to see clearly an object that is 25 centimeters in front of the eye. Okay, so this is a person that can't see things close by. So this person cannot see things up close. So we want to create images of objects at the normal near point of 25 centimeters, right? So we need to take objects that that are up close and then create images at that normal near point, right? Well, we want to take objects that are at the normal near point and then create images for them where the person can still see at 232 centimeters. Okay, so in other words, we want the object to be at 25 centimeters. That's the best case, right? We want to make sure that we're restoring their vision to normal. And we're going to do that by putting an image at where they can still see clearly at 232 centimeters. And it's negative because it's on the same side as the object. Okay, so then we'll just use the image formula for thin lenses and go ahead and solve for f. And we get 22.6 centimeters. Okay, so that is the focal length of the corrective lens for this hyperopic eye. And it's a positive focal length, which means it's a converging lens. Okay, and if we want to find the power, we just take the reciprocal of that, which is just then converting this over to meters. Make sure, because you can express this in centimeters, we usually do, but the diopters are based on meters. So notice I converted my centimeter expression over to meters, raise it to the -1 power, and I get 4.43 diopters. Okay, let's do a series of quick concept questions. Make sure we're clear on what type of lens is what. Now, these are most valuable for you to do yourself, but just consider this the check. Make sure you got them all. All right. So question 1. Again, pause if you need to. Make sure you can answer these all by yourself. Question 1. If the near point of your eye is at 75 centimeters, you have what type of vision? Okay. This means you cannot see things up close. That's farsighted, which is hyperopia. All right, question 2. What type of vision requires the use of corrective lenses that function much like a magnifying glass? Okay, well, a magnifying glass is a converging lens, and so that means we're correcting farsightedness, hyperopia. Okay, all right, question 3. If your vision is improved with lenses that look like this one here, all right, then you must have what type of vision? Well, what type of lens is this? That's a diverging lens. Diverging lens correct nearsightedness, so that means you have myopia. Okay. All right, let's do another problem with corrective lenses. The far point of a certain myopic eye is 65 centimeters. All right, so this is a person that is nearsighted. Okay, they can't see anything past 65 centimeters. So then it's far away, it's just blurry. That's not very far. Find the focal length and power of the eyeglass lens that will permit the wearer to see clearly an object at infinity, and assume the lens is worn 2.5 centimeters in front of the eye. So in example 1, we assumed a contact lens, but here we're not. We're actually using eyeglasses. And notice there's an extra distance here. How do we deal with that? right? So myopic is the key word here. So we know right away that this is nearsightedness, all right? That means that we want an object at infinity, not at 65 centimeters, all right? And a desired image at that limited far point of, well, 65 centimeters. So we want the image to be at negative 65 centimeters, negative because the image is going to be on the same side. It's a virtual image, all right? But the thing is, we don't want the full 65 because we got to account for the fact that the corrective lenses is worn in front of the biological eye by 2 centimeters. So that means we want to put the image 63 centimeters away from the actual eye, okay? Because the lenses are already 2.5 centimeters in front. That's why I subtracted that well, here I subtracted 2 centimeters. I actually should have subtracted 2.5. So please excuse my numerical inconsistency there, okay? So, all right, so that's from the lens. So we're going to go ahead and solve for the focal length with that information, just as we did in example 1. But the difference here, of course, is that our image is formed at infinity, which makes for a really simple equation here, because I just have just 1 over something raised to the negative 1 power, which of course is just the number itself. So I get negative 63 centimeters as my focal length. Notice it's negative because after all, this is myopia, and myopia is all about diverging lenses. All right, so I can then find the diopters as well. All right, and that's just taking the reciprocal, and that gives me a negative 1.59. Okay, that's great. But what about if I replace my lenses with contact lenses? Because in that case, my diopter value of the contact lenses will not be exactly the same. So the diopters of contact lenses are always slightly different from eyeglasses because of this distance. Okay, so in that case, now I want my focal length still to equal s prime, but now I want it to equal negative 65 because I'm not subtracting that extra distance. Okay, and so that means that my value of diopters will be 1 over 0.65, which now is negative 1.54. Okay, so there we have it. Okay, so now let's move on to a problem that involves a microscope. So we have a biological microscope with a standard length of 160 millimeters. I will always, in any of my example problems, give you the length of the microscope. However, there is a standard. Sometimes problems will just say a microscope or a student's microscope, and you're supposed to assume it's 160 millimeters. Okay? And anyway, so this particular microscope has an objective lens labeled 20x. That means it has a 20 power magnification. And the question is, what is its focal length? That would be the objective lens's focal length. All right, so 20x means that the object is, has a height that is 20 times taller, all right? And that means we can go ahead and say, okay, well, in that case, I can just solve for the focal length by just taking negative L over M1, all right? And again, this is because the magnification in the total magnification of a microscope for the objective is always expressed as a non-angular magnification. In fact, the only magnification in the set of notes that is a non-angular magnification. And so that's why I'm using non-angular magnification. Okay, but anyway, so with our approximations, that focal length is just equal to negative L over M1. There's our length, and then there is our distance, our original magnification. The negatives cancel out, so then we get a focal length of 8 times 10 to the negative 3, or 8 millimeters. All right, okay, a short focal length like we should expect to get 20-fold magnification on that lens. The total magnification could be more than 20. It could be 2,000 if the eyepiece had 10, because we have 20 times 10. Okay, but we'll see examples like that. Let's take a look at another microscope problem. Example 4. A student uses a microscope with a length of 160 millimeters to view an amoeba. If the objective has a focal length of 1 centimeter, the eyepiece has a focal length of 2.5 centimeters, and the amoeba is 1.1 centimeters from the objective, what is the microscope's magnification? So in this problem, we're going to make an approximation, which we're not in the other two, which is kind of interesting because, of course, I made a big deal about why those approximations are justified and useful to have a microscope that's only dependent on the physical parameters of that microscope. But most of the time in the problems, I will not be using them in order to show you other concepts. Okay? So here we will use the approximation that S1 equals F1, right? So that the object distance to the distance to the original object is equal to the focal length of the objective. And that means that we're just saying that 1.1 centimeters is about equal to 1 centimeter. After all, these were the two values that were certainly closest to each other of the stated values, and we're just saying, nope, we're just going to treat them as one number, all right? Treat them as 1. So then the total magnification of the microscope is the product of the magnification of the eyepiece and the objective in the eyepiece, all right? And so then, of course, we're going to write it this way using all of our approximations, and then we'll just plug in our values, all right? Because we know the focal length of the objective is 1 centimeter. We know the focal length of the eyepiece is 2.5. We know the length, and we certainly know the human near point. So we're all done, plug and chug, and we get negative 160. It will always be a negative value because, indeed, the final image is a inverted image that is virtual, right? Now, of course, there are plenty of virtual upright images, but since this is a secondary image, it is both virtual and inverted, okay? All right, example 5. Now, we're not going to make as many approximations in this one. The eyepiece of a compound microscope has a focal length of 2.8 centimeters, and the objective lens has a focal length of 0.74 centimeters. If the object is placed 0.79 centimeters from the objective lens, calculate A, the distance between the lenses when the microscope is adjusted for a relaxed eye, and the total magnification. All right, so this is interesting, because here we're not going to say that these two numbers, even though they're close, are equal. Okay, so here we'll not make the approximation that the original object is equal to the focal length of the objective. Thus, for the objective, we'll actually use the lens formula, the image formula from lenses, and solve for the image location that's formed by the objective. Plug in our numbers because we do know the focal length of the objective, and we also know where the image is being formed due to where, or rather, we know where. Yeah, so we know where the image is being formed. Okay. All right. Oh, that's right. Because this is, I see. Because this is the object, right? This should not say S prime 1. This should just say S1. So that's an important correction there, because that is the object distance, and we know that the object distance is placed at 0.79. Okay, and we know the focal length of the objective. This is say F1. Okay, but anyway, so when we find the object, or rather the image location formed by the objective, we find that it's 11.7 centimeters. All right, that's going to be most of the length, because after all, we are trying to find the length here, the distance between the lenses. We're trying to find L. So we know this is going to be most of the length, but not all of it, because we're not going to assume that that's it, right? Instead, we're going to say that the length is equal to that distance plus the focal length of the eyepiece. But the good thing is we know that focal length. All right, and we know that since the relaxed eye adjustment means that S2 prime just equals infinity. Okay, and what I'm saying there is relaxed eye means that I can assume then that that extra distance to sum up L is exactly just equal to the focal length of the eyepiece, because we know if we put the image formed by the objective at the focal length of the eyepiece, then we get a final image, a secondary image that's infinitely far away, but we know that's what we want because we were told we were working with a relaxed eye. Okay, so S2 equals F2. All right, so then I can plug in my value for the focal length of the eyepiece and find that the total length of the microscope is 14.5 centimeters. And indeed 11.7 centimeters, where the image was formed, was most of that. Okay, all right, so then finally I can find the total magnification. Okay, so this is going to be M1 times M2. All right, so we'll go ahead and use our approximations here and plug in our values and get negative 175. Okay, now, could we have, foregone this and not use some of our approximations? I suppose so, because we do, after all, know, we know S1, right? We actually know the value of S1, so we could have, for a slightly greater accuracy, we could have plugged in S1 here instead. S1 instead, okay? But I would accept either. So finally, we're going to use perhaps fewer approximations, but more importantly, we're not going to use a relaxed eye. So we're finally going to use that subtle difference between angular magnification for a relaxed eye versus with a focused eye at the human near point. So let's take a look at it in the context of a microscope. So a microscope has a 15 times eyepiece, 15 times magnification eyepiece, and a 50 times objective lens in terms of magnification. They are 20 centimeters apart, that's L. We want to calculate the total magnification, the focal length of each lens if the final image is located 25 centimeters from the eyepiece, which is the near point of a normal eye, okay? So here we're using a microscope to get that extra +1 in terms of its magnification power. In this case, the total magnification is not just M1 times M2, but M1 times M2 plus 1. See, there's our one more. And the one more just shows up on the angular term, because after all, this was a non-angular magnification. Okay, the negative is because inverted, and here because the secondary image is at the near point. Okay, that's where the +1 came from, and we saw the derivation of that back in the key equations. Okay, so please refer to those, and then we'll plug in the values that were given, the 50 and the 15 respectively. All right, and of course the 15 becomes the 15 plus 1, and we get negative 800 is our magnification power. Wonderful. Okay, now let's look at part B, because part A was relatively simple. The focal length of each lens if the final image is located 25 centimeters from the eyepiece. Okay, so now, because we realize we're given both the magnifications of the lenses, but we're not given their focal lengths. So how do we go back and find them? Well, we got to work backwards from what we know in order to find the focal lengths. So what we know so far is that the angular magnification of the eyepiece, M2 plus 1, is just equal to 25 centimeters, human near point, over the focal length of the eyepiece plus 1. Well, that allows us definitely to solve for the focal length of the eyepiece because we know that M2 is 15. Okay, so we'll go ahead and set that up and solve for M2 because the plus 1's cancel. And we end up with 1.67 centimeters. So we got one of the focal lengths out of the way really easily. It will take a bit more steps to get the focal length of the objective. All right, so there we have the eyepiece focal length. So now we want to find where the primary image, that's the image formed by the objective, is formed. So we use F2, and we use the fact that S2 prime equals negative 25 centimeters, right? Whereas, of course, in the previous example, S2 prime equals infinity. All right, so let's start, express the image formula here. And go ahead now and solve for S2, because this is where the actual object that the eyepiece is focusing on is formed. Okay, so let's go ahead and find where that's located. Plug in our numbers, plug in our recently found focal length, plug in the human near point, which was stipulated by the way the eye is working with this microscope, and we get 1.57 centimeters. Okay, but what are we going to do with that information? What are we going to do with the information about knowing now where the primary image is formed? Well, since this is the object of the eyepiece, but since it's the primary image, that means that this is tied to the objective lens. All right, so then we can say that the total length is just going to be the sum of S1 prime plus S2. There's no approximations here, okay? So, other than the ones involved in the thin lens formula, but no additional microscope approximations. Okay, so then we're going to find S1 prime. Now we're just going, because here we're just finding the image formed by the objective lens. All right, and then we'll go ahead and find it, and it's 18.44 centimeters. And now we can definitely go back and then you relate that to the magnification of the objective, right? Because now we're just going to do S1 prime over S1, okay? Which then we can solve, which means we can solve for S1, okay? Because now we're finally solving where the original object is located. Go ahead and do that, and we find that it's 0.369 centimeters. But why are we doing all this? In order to find the focal length of the objective. But now we're really there, because look, we've pieced everything together. We found the image distance from the objective. We found the object distance from the objective. Once you know both those, you can find its focal length. So there we go. We're finally going to find the focal length of the objective, plug in our values, and it's 0.362 centimeters. We found both the focal lengths, all right? But it was really interesting how this problem, without any approximation, required us to work backwards through using the image formulas and the definitions of the magnification. Okay? All right, well, finally, let's wrap up this lecture by talking about two examples that relate to telescopes. All right, so these are, as I said earlier, a bit easier than any microscope problems. All right, so example 7. The objective lens and the eyepiece lens of a telescope are 1 meter apart, right? The telescope has an angular magnification of 50. They're usually not that great, the actual magnification power of telescopes. And find the focal lengths of the eyepiece and the objective, okay? So how do we do that? Well, because the approximate location of the image formed by the objective is at the eyepiece, or at least at the eyepiece focal length, we can then say that F1, the focal length of the, well, actually here, I'm even going further. I'm saying it's formed at the eyepiece. And the reason there is I'm just saying that F2 is much, much smaller than F1. So the focal length of the eyepiece is much less than the focal length of the objective, and therefore, I'm just saying then that the focal length of the objective is about equal to the whole length, right? So that's what I'm saying here, all right? So 1 meter, all right? And thus, the total angular magnification of the, well, telescope is then just going to be F1 over F2. We know the total magnification, we're told it's 50. So then I can go ahead and find F2, which is going to be the focal length of the eyepiece, and we find that it is 2 centimeters, which meant that our approximation here, we're basically just saying that all we said was that 98 centimeters is approximately equal to 100 centimeters, which allowed us to get this number in the first place, right? So, but then we found out, that, yeah, okay, was it a reasonable approximation? Yeah, I think so, right? So there we have our two different focal lengths, one very large for the objective, one very small for the eyepiece. Overall magnification, decent. Now, again, we shouldn't expect big values for the angular magnification of a telescope, because telescopes, although they do magnify, are more about collecting light over prolonged periods of time and getting images that way, okay, of things that are very faint. Our final example, example 8. The minimum distance between Earth and Mars is 54.6 times 10 to the 6 kilometers, right? So 54 million kilometers. And the radius of Mars is 3.39 times 10 to the 3 kilometers, all right? So 3,390 kilometers. What is the angular size of Mars as seen by the naked eye? Okay, so the angular size here, or now we don't have to use tangent theta. I could just use that just theta is equal to this ratio, all right? But we can use tangent as well and get a number that is basically about the same. Like this is an unnecessary step to use inverse tangent, as I do here. Again, you could just take the ratio, but it's fine either way, okay? So, and again, I just took the ratio of the, one side of the triangle, which is the actual, the radius of the planet. So it'd be like this. So the radius of the planet here, and the distance of the planet there, right? And of course, then that gave me my angular size of the planet. And I get 6.21 times 10 to the negative 5 radians, which is equivalent to basically, 4 thousandths of a degree, or 12.8 arc seconds. And that's because there are 60 arc minutes per 1 degree, and then there are 60 arc seconds per 1 arc minute, which means that there's 3,600 arc seconds per 1 degree, which is where I get this conversion from. Okay, so great. There we have our angular size of Mars with the naked eye. All right, but now let's use a telescope. Okay, so we're going to use a telescope with an objective focal point of 81.5 centimeters, so a long focal point or long focal length. And then we have a eyepiece focal length, a short one, of 8.35 millimeters. All right, so the magnification of this telescope, we can simply plug in those focal lengths and find out that it's 97.6. Then we're going to go ahead and find the angular size by just using the definition of the total magnification of a telescope, all right, which is just going to be that factor times whatever is the angular size of the naked eye, because theta here is the angular size of the naked eye, the unaided eye. And then we find out that it's quite a bit larger, right? Instead of 6.21 times 10 to the negative 5 radians, it's 6.6 times 10 to the negative 3, right? Which we should expect should be about 100 times larger, right? Because that was our magnification factor. And we can convert that over, right? Convert it over to degrees, or even find out that now it should be measured in arc minutes. Okay, well, that concludes our lecture on corrective lenses, microscopes, and telescopes. In other words, optical devices, and concludes our overall unit on optics. All right, well, I hope this lecture has been informative and interesting. Thank you so much for watching.